All right, thanks so much. Thanks for the invitation. So when I saw I was coming to this conference and I looked at the titles and abstracts, I thought, oh no, the thing that I'm going to talk about has nothing to do with any of the other talks in this conference. This is just a totally, completely unrelated subject. It just happens to be, there's connections to work of Peter Greenberg. And then I came here and I started watching the talks and I thought, oh my goodness, actually there's a point of substantial overlap between this subject and just about every other talk in this conference. These Gauss-Biot invariants actually look a lot like the Dane invariant and scissors congruence. They land in similar looking groups. When you compute scissors congruence, you end up thinking a lot about the homology of Lie groups made discrete. And that's quite closely connected to foliation theory. And then finally, Thompson's group V just straight up shows up here. So that's a pretty direct connection. So on the surface, this is just going to be a totally different topic. It's totally unrelated to everything else in the conference. But just underneath the surface, there's all kinds of connections. All right, so a lot of this is based on joint work. I'm just writing out all the names now, because as you can see, it takes a long time to write them all out. So there's the group with Anna Marie Bowman, Tina Gerhardt, Mona Merling, and Ina Zakharevich. We like to refer to that as Big Mamas for short. It's convenient. Sander Coopers, Ezekiel Leman, Jeremy Miller, and Robin Sroka, two of which are in the room right now. So we sometimes refer to that group as Cool Mamas to disambiguate, right? Big Mamas versus Cool Mamas. I'm actually not going to talk a lot about the work of this group, but there is ongoing work of this group on defining higher versions of the Dane invariant. So it's Kuiper, Klang, Murley, and Vidic. The way we refer to that is kitty cat meow. It's a work in progress. And then finally, there's some joint work that's in progress with Jin Li and with Fangji Liu. And I don't have a fun acronym for those pairings yet. Open to suggestions. OK, so like I said, this is on the surface a totally disconnected, unrelated topic to all the other topics. So let's start over from the beginning. So I'm going to let xn refer to either Euclidean geometry, hyperbolic geometry, or spherical geometry. Other settings are possible, but it's enough to focus on these three. And in particular, I'm actually going to focus the most on Euclidean geometry. So you can just picture Rn with its usual metric. And then I'm going to define a convex polytope to be a convex hull of any finite set. So if I'm in spherical geometry, I have to be a little bit more careful and say that that finite set's in an open hemisphere, so that convex hull makes sense. And I'm also going to assume that it's non-degenerate. So it's not properly contained in any subgeometry of a lower dimension. So if in the Euclidean plane, for instance, I'm thinking of triangles, quadrilaterals, pentagons, and so on, but I'm not allowing line segments, and I'm not allowing points. All right, so that's what I mean by non-degenerate. OK, and then a polytope is any finite union of convex polytopes. Any finite union at all. No conditions on that. Oh yeah, they can overlap. But you could always subdivide them further so that the interiors don't overlap. So without loss of generality, it's with non-overlapping interiors. So this allows us to make non-convex shapes like that. It allows us to make disconnected shapes like that. In spherical geometry, the entire sphere is an example of a polytope. OK, so that's what I mean by a polytope. All right, so we want to talk about scissors congruence. So what's a scissors congruence? I don't think I have enough room. Let's continue the story on the next board. Well, you can kind of imagine what a scissors congruent should be, right? It should involve taking a pair of scissors, cutting up your polytope into finitely many pieces. The finiteness is important. And then rearranging those pieces to make another polytope. So a scissors congruence is, I take, and this is from one polytope P to another polytope Q. So I take P and I decompose it into finitely many polytopes whose interiors are disjoint. So they're only allowed to overlap on their boundary. I'm basically ignoring the boundaries here. I really care about the interiors. Then I apply isometries, GI. It can be a different isometry for each piece. That's what's significant about this. And so that gives me some union of the images of these polytopes. And then I assume that that union is Q, and again, the interiors are disjoint. So that's what a scissors congruence is. It's a way of cutting up a polytope into pieces. Uh-oh. We'll try to get that later. It's scary down there. So it's a way of cutting the polytope up into pieces and rearranging the pieces. So you can imagine lots of examples of these. Like maybe I take a square, that's P. I cut P up into two pieces, P1 and P2. And now I'm going to move them differently. So maybe I'll move P1 here. And maybe I'll move P2 here. And now altogether, that'll make Q. So in this way, I can cut up and rearrange. I can change one polytope and really change its shape in a lot of different ways. But there are some things that don't change, right? So for instance, the area of that polygon is not going to change. In fact, it's a really cool theorem that in two-dimensional Euclidean geometry, P and Q are scissors congruent. So by that little twiddle, I mean scissors congruent. If and only if they have the same area. Cool theorem. You can prove it by elementary techniques, but it's not easy. It's maybe like at the level of an Olympiad problem. So if you're bored and you hate the rest of my talk, think about why this theorem is true. It's a fun thing to think about. OK, so generalizing this, when we do scissors congruence, before I do that, let me just say one more thing. So I said that GI is an isometry here. I could also fix some group G acting on the geometry, preserving the geodesic subspaces, in other words, the subgeometries, and therefore preserving the polytopes. And then I could do the same thing. So I could ask for GI and G, and that's an example of what we call a G scissors congruence. So there's lots of variations on this problem. Yep?
Do polytopes have to be like two-manifolds, or can they be like multiple dimensions?
Oh, does it have to be two-dimensional? No, I could go up to n-dimensional Euclidean geometry and do the same kind of manipulation here. So actually, like the really kind of marquee work on scissors congruence in the 20th century was in dimension 3. So we thought about three-dimensional polyhedra, and when can I cut and rearrange one polyhedron to make another? This is the subject of Hilbert's third problem. It was listed 23 problems. Thank you. OK, so for instance, just to give some examples of this more generalized problem, G could be Rn, and it could be acting on Euclidean space by translations. That gives what's called translational scissors congruence. Turns out it's quite a bit easier to compute. We know a lot more about that case than the general case. I could also, I don't know, let me just pick an example at random. G could be PSL2Z, I guess, acting on the line or in the circle, as in Yash's talk. Right? So there's lots of examples of groups acting on these geometries that you could consider this problem for. All right, so what do we do when we do scissors congruence?
On the hyperbolic space should be asymmetric.
Yeah, but it doesn't necessarily have to act by isometries. It only has to act in a way that'll preserve the geodesics, so that it preserves the polytopes. So yeah, so for the hyperbolic plane, any action that has that property, you can think about this problem for. If you take the hyperbolic plane and all isometries, or even orientation preserving isometries, I think, this theorem is also true in that setting, although it's a lot harder to prove. It's much easier to prove in Euclidean geometry. All right. Oh, I haven't stated the question yet, so I haven't even, but you probably can guess what the question is here, right? Like, I give you this notion of equivalence between polytopes. The question is, well, like, okay, how do the polytopes split up when I apply this equivalence relation? So the classical question is classify P up to scissors congruence. Such as, that can mean different things, but it could mean, for instance, give a list of things that you compute, and if you computed all of them, you can tell if two polytopes are scissors congruent or not. Right? Just like in knot theory, you want to distinguish knots, right? So like come up with some set of invariants that you can compute that tell you if two knots are the same or not. Okay, that's the classical question. The modern question goes a little bit beyond this and also looks at the scissors congruences themselves. So not just what are the polytopes, classify the scissors congruences themselves. So not just when are P and Q scissors congruent, but what actually are all of the transformations I can use to get from P to Q. So of course, this is a group theory question because I can define this group aught of P. And sometimes I'll put a subscript of G in here if I'm changing the group G that I'm using. So this is the group of scissors automorphisms. In other words, self-scissors congruences from P to itself. So elements in this group are scissors congruences from P to itself. To give you a simple example, take a rectangle, cut it into two pieces, move that piece over there, and then move the big piece over to the right. And you've reassembled the same rectangle in a different way. By thinking about this example, you can already see right away this is an uncountable group. Right? So this group is quite big, and we didn't even try anything fancy. That's about the simplest thing you could possibly do. There's a minor technical point here. So this is the definition of a scissors congruence, but two of these might give the same element in that group. They give the same element if, well, let me just say how you can generate the equivalence relation. I can take one of these pieces, and I could cut it up into two smaller pieces, like that. And if this isometry was G1, if I apply the same isometry to each of those two smaller pieces, then this is still considered to be the same scissors congruence. Yeah, question?
Can we get a different color than green, please?
Absolutely. Thank you. How's yellow?
Nice. Looks great to me.
Excellent. So yeah, so if G1 was originally applied to this piece, I could cut it up and apply G1 to each of the new pieces. I'm going to consider that to be the same scissors congruence. So it's pictures like this, but up to subdivision of the pieces. That's what an element of this group is. Yeah, question? Yeah, you can use any isometry. So this example that I drew here is a translational scissors congruence, because I only use translations. Let me give a more general example. All right. Oh, hey, we can go simultaneously. Wait, no, you stay there.
But is that the same automorphism if you took those, if you subdivided and you switched the pieces?
That would be different, because now each piece has a different isometry acting on it. I'm doing that switch map, and then I'm applying G1. So that composite is now a different isometry.
Do you need the pieces the question is connected?
Nope, they just have to be polytopes. But up to this subdivision, without loss of generality, they may as well be convex polytopes. Yep. Good, good. It's good to make sure everyone is OK with what is the definition of this group, right? Because this is a very important group in this talk. OK. Yeah, let me give a bigger example. Let's take a triangle. Let's cut it like this. And now let's make that more dramatic. So that's like a tiny triangle and a big one. And now let's move the tiny triangle down here. Let's move the big triangle up here. And let's take the rectangle and rotate it. Right, that's another example of a scissors automorphism. OK. So to spell this out explicitly, so in E1, two polytopes are scissors congruent if and only if they have the same length. That's quite a bit easier to prove than that cool theorem. Right? You can probably convince yourself of this right away. But so that's an answer to the classification question. Right? They're scissors congruent if and only if they have the same length. And the cool theorem is another example of an answer. They're scissors congruent if and only if they have the same area. So the automorphism groups of a interval, let's say the interval from 0 to 1. So this is a variant of the interval exchange transformation group. I don't know if there's a standard name for it, but you could call it the interval exchange and flip transformation group. So you cut your interval into pieces and you rearrange them, but you also allow flips. You could also restrict your symmetry group, right? So I could just allow only translations instead of translations and flips. And then that's the group of interval exchange transformations. You can also think about how Thompson's group V is also an example of one of these scissors automorphism groups. Right? Just think about you have to restrict the polytopes a little bit, and then think about what the group G would be in that case. I'll tell you later in the talk.
You didn't get the piecewise isometry group in general. If that's one dimension, two dimension, you call it piecewise.
Oh, yeah, that's right. These are also called piecewise isometries. PWIs. Yeah, so that's, we didn't know that at first, but then we found a bunch of papers from earlier that call them piecewise isometries. So what we're studying is the group of piecewise isometries. And I want to emphasize these are not homeomorphisms. We are actually allowing ourselves to, pull the different pieces apart and stack them together in a different way. So that makes this a little bit different from Greenberg's work on piecewise SLNZ homeomorphisms. This is like more of the V version of that instead of the F version of that, to use Thompson group language. All right. How are we doing?
Just a random question.
Yeah.
The one with flips is different than like up to isomorphism. Do you know that those two groups are not abstractly isomorphic? I asked because V with flips is accidentally isomorphic to V.
Oh, that's really cool. Yeah, we know. So I'm going to mention this later, but let me mention it now. The abelianization of interval exchange transformations is R wedge product over Q with R. And this one's abelianization vanishes. OK, I didn't flip them. Yeah. So we know that they're non-isomorphic. All right. So we've said what a polytope is. We've said what scissors congruence is. We've kind of set the stage with the main problem. Right? The main problem is classify the polytopes and understand something about these groups. So now what I want to do next is how do you actually attack this main problem? What's your strategy? The strategy probably has already occurred to you if you thought about it for a little bit. And if you come from an area like algebraic topology or knot theory or something else where this kind of strategy is very common, the strategy is cook up some invariants. Right? So especially, this is important because I want to be able to show that polytopes are not scissors congruent. To show things are not scissors congruent, a completely insane way to go about it would be to try to run through every possible scissors congruence from one to the other and show that they don't work. Right? That's insane. There's no way that'll work. So you need something more indirect. Right? So I compute something where if I show if the values are different, I have abstractly shown that they're not scissors congruent. Right? OK, so let's just spell out what these invariants look like. I'm going to call them K0 invariants for reasons that will become clear later. So a K0 invariant is an abelian group. I'll call A rule that sends every polytope to some elements in that abelian group. So that's the value of the invariant in that abelian group. And then I want it to be additive. So it's going to be the sum of the values of the pi if I have a decomposition like there, if P breaks up into finitely many pieces with disjoint interiors. So I'll go through a little portal here, and then this is silly, but I want to do it. Come out of this portal here and then point up there. OK, good. That was fun. All right, and then finally, if I apply an element in my group, then that should not change the invariant. OK, so that's the definition. That's just a definition of properties I'd want an invariant like this to have. So of course, this implies that if P and Q are scissors congruent, OK, this is bad notation. So if they're scissors congruent, then they must have the same value. And so contrapositively, if they have different values, you've shown that they're non-scissors congruent. Great. So what's an example of this? So probably the first example that comes to mind is volume, right? Volume of P in R, that satisfies these properties. At least, OK, so I made the problem very general, but at least if G is some group that preserves volume, such as the classical isometry group. So in E1 and E2, this is basically it. I say basically because you could do funny things like I could take the volume times 2. OK, right? But I'm not really getting anything meaningfully different from the volume. In E3, though, it turns out there's more. So in E3, I can define the Dane invariant. It's a really cool construction if you've never seen this. So I'll call this D of P. It's an element in the tensor product of R with R mod pi z over z. So formal products of these things. You can move the z's back and forth, but nothing else. And it sends each polytope to, I could put it up here. So D of P is the sum over the edges of the length of that edge as a real number, tensored with the dihedral angle. So geometrically, this is the angle that's formed between the two faces of your polyhedron that meet at that edge. And I think of that as an element in R mod pi z. So I'm using radians, of course. If you want to use degrees, you could say R mod 180z. But why would you do that?
That would change how Z acts on it, right? How does Z act on R mod?
Oh, this is as an abelian group. So it's a modulo over Z, so Z acts by repeated addition. So in other words, you multiply by integers. All right, this is just an abelian group. There's no, I'm not putting any further structure on this. OK, so another exercise, if you're bored and you hate the rest of the talk, convince yourself that this is actually an invariant. Right? Think about, in particular, if I take a polyhedron and I cut it into two pieces, I'm going to create some more edges. But why did the Dane invariants of those edges add up and create the Dane invariant of my original polyhedron? It's a fun exercise to think about. There's essentially three cases you have to think about. Cutting an edge so that the length splits up, cutting an edge lengthwise so the angle splits up, and creating new edges by cutting through a face. And that's where the mod pi z becomes really relevant. People are thinking about it. OK, good. That gives me a chance to look at my notes. Oh, there is an analog in E2, but it vanishes. So you could sum over all the vertices of 1 tensored with the angle at that vertex. And then that adds up to a multiple of pi when you add over the polygon, so it vanishes. Yeah, of course. Oftentimes I give this talk, and then I'm like, what's an example of an invariant? And some joker is like 0. Like, OK, cool, good. Good mathematicians. All right. Great. So we have volume, and we have the Dane invariant. And you can compute the Dane invariant of any cube, or more generally of any box, any product of 3 intervals, is 0. But the Dane invariant of a regular tetrahedron is non-zero. So this uses the fact that the dihedral angles here are inverse cosine of a third, another fun exercise. And this is not a rational multiple of pi. That might be too hard to be an exercise. Okay, but so even if I take a cube and I take a regular tetrahedron, even if these things have the same volume, there is no way they can be scissors congruent, because there's this funny thing that you can compute for them, and it takes different values for the cube and the regular tetrahedron. Yeah, so I should mention this was Dane's solution to Hilbert's third problem. Hilbert asked if the volume was enough, essentially. And Dane showed that no, the volume is not enough. You also need this Dane invariant. All right. Well, arguably that was a solution. So Hilbert asked, OK, so if two, he didn't exactly ask this, but it's more or less the same as this. If I have two polyhedra in three-dimensional space and they have the same volume, are they scissors congruent? And Dane showed, no, that's not enough. You need to also, this invariant is an obstruction. But that kind of leads to a natural question. Well, is the volume and the Dane invariant enough, right? Or is there more? In other words, how far do we have to go until we get a complete list of these scissors congruence invariants? So because of that joke about, I could always take 2 times the volume or something like that, you kind of have to phrase this question correctly. Right? You can't just say how many scissors congruence invariants there are. You have to organize them. And it turns out there's a really clean and really nice way of organizing them. And the idea is to use K-theory. K-theory is the universal invariant. So what's K-theory? I define K0 of my geometry to be all scissors congruence classes of polytopes. So I'll write P in square brackets to note that it's the scissors congruence class of P. That's an abelian monoid under disjoint union. I can add them together, but I can't subtract. So then I take the group completion of that. I formally add negatives to it. That's the definition of K0. So every polytope, by definition, gives a class in K0. And pretty much by construction, this is an invariant. This is a K0 invariant, as I defined it. It's pretty much, this is kind of like in knot theory, where it's like, I want to define the universal knot invariant. OK, take the isotopy class of the knot. Right? So you shouldn't be super impressed by this, right? This is really just an organizational principle. It tells us if we want to answer the question, what we should be doing is computing this group. I didn't say how it's universal, right? If I had any other invariant in some abelian group A, I could send all of the generators to their values there. And that would give a unique homomorphism like this, through which the invariant factors. So in this way, if you've computed this invariant, you've really computed all invariants. Okay, so it's not impressive, but it's a really nice idea because it organizes the problem and clarifies it. What you really want to do is compute this group. All right, so for example, K0 of E1 is R, corresponding to the length. So this corresponds to the fact that line segments up to scissors congruence are classified by their length. By the way, I should mention there's this theorem of Zylov that says that if 2 classes are equal in this K0 group, then they actually were scissors congruent. Right? So this actually does correspond to the fact that polytopes in E1 up to scissors congruence are given by length. The fact that we have negative reals is because we formally added those negatives. That makes it an abelian group, so it makes it easier to compute and work with. But we didn't lose any information. So in two-dimensional geometry, you again get R, but now it's area. So this captures that cool theorem from earlier. I might have erased it already. Oh, no, there it is. Right, this captures the cool theorem from earlier that polygons up to scissors congruence are given by area.
You mean to say E2?
I did, thank you. I guess that was also a true statement before, but kind of weird to say it twice. All right, so now in E3, we have the volume. And now we also have the Stein invariant. OK, so it's a theorem of Seidler, reproven algebraically by Jessen, that the volume and Stein invariant are enough. Those are complete invariants for three-dimensional scissors congruence. And you can state that theorem very elegantly by just saying this homomorphism is injective. Yeah, question, comment? In 3 dimensions. Yeah. So in 3 dimensions, you have the volume, you have the Stein invariant, and those are complete invariants for scissors congruence. Similarly for E4, there's a similar injective homomorphism. Yep.
It's also surjective.
Hmm?
It's also surjective.
It is not. But we know what the co-kernel is. So there is an exact sequence. So in that sense, we do have a complete computation. Whatever computation means here, this is some uncountable rational vector space. I think this does count as a complete computation of this group. So we know the answer in degrees 3 and 4, but in degree 5, it's open.
You mentioned Z is for all the congruence, or
Oh, yeah, this is for G as the isometry group.
yeah, no,
So that'll be the default assumption that I'll use.
no, but you wrote for the theorem Z.
Yep.
This one is all
Oh.
through, you mean?
Yeah. No, not for all. So it's true for the full isometry group. It's not true for all possible G. There are some assumptions on G that I don't want to go into in the middle of the talk, but I can tell you afterwards if you like. If you do ideal polytopes in the hyperbolic plane, then the theorem fails. So you have to have some ability to translate things around, cut things up into small pieces, and then put the pieces inside other polytopes. And if you have a point that's stuck at infinity and you can't pull it away from infinity, then you can't necessarily, then you can't do that.
I'm sorry, can you, again, can you just say again what it says, why it's not topologous?
So by construction, if they're scissors congruent, then their classes in K0 are the same. Zylev's theorem says that you can go back. So if they were the same after group completing, then they were actually the same before group completing. That's not obvious because group completion is sometimes not injective. Yeah, it is in this case. OK, so there's the strategy for the classical question, right? Is there a similar strategy for the modern question? Right? Can we also use invariants to count scissors congruences?
Why can't you do it in 5?
Hmm?
You didn't explain why 5 is impossible.
It's an open problem. I mean, I don't want to claim it's impossible. Maybe you have an idea for how to do it. But no one has been able to do it. And this result is from 1972. And this result is from 1968. And who knows when this one will be worked out. This one is from, this is attributed to Wallis-Boyer and Gerwien in 1807, but arguably it goes back to ancient Greece and China. So this is an older theorem. I don't want to put a year on that. I'd have to think about which calendar to use.
Does that mean in this whole period of the last 50 years, there made no progress on the 5-dimensional case?
I wouldn't say no progress, but we don't know what the answer is. So we do know that there's a 5-dimensional volume, and there's 2 Stein invariants that are non-vanishing there. And so one version of that question is the map to that volume and those Stein invariants injective? we know how to reduce that question to some hard calculations in the homology of Lie groups made discrete. So we actually do know an awful lot about this question. We just don't know the answer. All right. This has been fun. We'll see how much I get to. It's fun to just talk about scissors congruence. I love it.
When you say 2 Dane invariants,
Yep. There's one for the 3-dimensional faces, and there's one for the 1-dimensional faces. So in general, all of the faces of even codimension will have their own Dane invariant. So as you go up in dimensions of your geometry, you'll progressively get more and more Dane invariants.
so you mean the Dane for E4, the Dane invariant is not analogous. It's exactly the original Dane invariant?
You sum over the 2-dimensional faces of the area of that face and the dihedral angle formed by the 3-dimensional faces that meet at that 2-dimensional face. Yeah. This is cool stuff to think about. I love it. OK, so right, this is all about the classical question. What about the modern question? Right? Can we use the strategy of invariance to attack this? So it turns out you can. And here's a way of thinking about it. So we'll define a K1 invariant in much the same way that I defined a K0 invariant up there. So again, it's going to be an abelian group. It's going to be a homomorphism from the scissors automorphism group to A for every polytope P. Seems rather strong, but OK. And then whenever P is scissors congruent to Q, I'm going to have this isomorphism between their automorphism groups. You can think of this as conjugation with the scissors congruence. I want the corresponding maps to A to agree along that isomorphism for every scissors congruence. And then finally, if I include P into P disjoint union some other polytope, that gives me an extension by identity map.
You're picking scissors congruence, so like between P and Q in order to induce the automorphism, right? Because you could
That's
also
right.
do a scissors automorphism of P beforehand, right? And mess it up.
So maybe I should say for all scissors congruences from P to Q, the induced map, the map induced by this commutes with the map to A. That's more accurate.
That's a lot stronger, too.
Yes. Yes. One of the theorems I'm going to tell you is that this is actually, although this seems ridiculously strong, it's actually quite easy to construct these. And then finally, if you extend by the identity, that also commutes with the map to A. OK, so yeah, thank you. I was hoping someone would point out that this seems ridiculously strong. Uh-oh. I think that's the oldest board. This seems ridiculously strong, right? But you might already know of an example of one of these K1 invariants if you have studied the interval exchange transformation group before. So here's an example in 1-dimensional geometry. The SAF invariant stands for Sa Nu Farthi. This is from Mi-Sung Im's talk yesterday. So this is for 1-dimensional Euclidean geometry with only the translation group acting on it, not the full isometry group. So this is a map from the interval exchange transformation group to R tensor R. As always, this is over Z or over Q, although it actually factors through the wedge product of two copies of R. And it extends more generally. So this is automorphisms of an interval of length 1. It extends more generally to automorphisms of an interval of any length. So what's this invariant? So it sends us an interval exchange transformation to a sum over the edges of the length of the edge. Gosh, this looks a lot like the Dane invariant, doesn't it? The length of that edge tensored with the translation distance. So you keep track of where along the line it translates. And you make it positive if it goes to the right and negative if it goes to the left. So to do a simple example, if I cut an interval into two lengths which are different, that's a y, x and y, and then I move the y over here, and I move the x over there, then my SAF invariant is going to be, OK, this is x. It moves to the right by y. And then I'm going to add a term for this. This is y. And it moves to the left by x. So that's x tensor y minus y tensor x. And that corresponds to, so that came from the wedge of x and y. Right, so that's an example of the SAF invariant. That can be defined for intervals of any length, and it satisfies all those assumptions. So a K1 invariant is not as crazy as you might think it is. All right. So just like for K0, there is a universal K1 invariant.
I guess it's in this wedge because you're always switching things, and so you're always going to get that sign.
Yeah, that's the intuition behind it. So you can show that you get an element of this, but it always comes from this. It had to be an automorphism, right? You had to start with an interval and end up with the same interval at the end. So there's a universal K1 invariant. You can construct it in a pretty straightforward way, just like we did for K0. And so that gives us a group, and we call that group K1 of the geometry. Right, so this is a group that has this universal additive or abelian invariant for these scissors automorphisms. And then you can keep going. So it turns out this definition generalizes. There's a K2 group, a K3 group, and so on. These are called the higher scissors congruence groups, or higher scissors congruence K-theory groups. They are, yep. You can also, there's a really conceptual way of thinking about them. I don't know if I have the definition of K0 here still. Oh, I do, OK. So K0 was the set of isomorphism classes of polytopes, and then you group complete it. To build these higher groups, you just take the space of polytopes up to scissors congruence, and you group complete that space. But then the homotopy groups of that are exactly these K groups. So in a sense, it's just like K0, you just think more homotopically. Oh, these are defined originally by Zakharevich.
Can you say K2 is, for example?
Well, it's not as direct as K1. Right? K1, I could give you this explicit formula. For K2, it is the second homotopy group of the space that you get by taking all polytopes up to scissors congruence and then adding negatives. So above K0 and K1, explicit formulas for these groups get harder. But here's not necessarily a formula, but sort of a connection between these higher K groups and the original group odd of P. So
Can you say what about the topology on that space?
yeah, it's a disjoint union of classifying spaces of these as discrete groups. So it's a disjoint union of KG1s. And then you can make that what's called an E-infinity space. So it has an addition that's commutative up to coherent homotopies, and you add negatives to that. All right. Here's another way of thinking about the significance of these groups. All right, so think about the homology of these automorphism groups. Well, I can take the polytope and I can just keep letting it get bigger and bigger and bigger, right? So as I do, it fills up more and more of the geometry, and I can take the colimit as p goes to infinity, or maybe it's better to say p goes to the entire geometry, right? So it gets bigger and bigger and bigger. It's not accurate to say until it fills up the geometry, but you know how limits work. Anyway, so you take the colimit of these groups, and it turns out that you get an algebra here, and it's rationally generated by, or rationally the indecomposables are, exactly the positive K groups of the geometry. So if you compute these K groups, it tells you something about the stable homology of these automorphism groups. This should be a familiar story if you've thought about algebraic K-theory of rings, right? This is just like how the K groups of a ring are related to the stable homology of the general linear group. Or if you like mapping class groups of surfaces, it's always fun to say mapping class group and see who perks up. You're outing yourself. The stable homology of the mapping class group is also described in terms of K groups like this, that you might call the K-theory of surfaces. And so this is how you can see where the Miller-Morita-Mumford classes come from. Right, so it's the same story here, only now we're talking about homology of these scissors automorphism groups, of which Thompson's group V is an example. You can maybe see where this is going. OK. So that's what the higher K-theory groups are, and that's their significance. Let's see. OK, let's see if I can do this. Yeah! Combination. Oh, that's right. Yeah, this is a scissors automorphism of the board. Oh my God, how did I not realize this? I'm applying a scissors automorphism to the board. Look at it go. Calculate its invariance.
Is this what you mean by the space?
Yeah, we're doing scissors automorphisms live.
Feel like you're putting technology.
Yeah, yeah. OK, so how are we doing? We've got 12-ish minutes left, and I've at least told you what the higher K groups are. Fantastic, right? I've set up the story, and now this was kind of the way things were a few years ago, that we had this notion of higher K groups, and we know that they have, well, we actually didn't quite know the significance to homology, but, and we had this big problem that we didn't really actually know how to compute any of these. So like, we kind of knew K0 of E1, we knew that all the way up to K0. Let me just write them down. So we knew these. And then we had question marks. And then what do we know about K0 of E1? I think we knew that. So Zakharevich computed K1 of E1. And then that was about it. So we have this whole system of groups. But we had very little kind of computational information about what these groups actually look like. But something very cool happened in the last few years, which is that we started to really understand how to break these down and start to give formulas for them. And as a result, we now know all the higher K groups in dimension 1. So this is the result of work with the Big Mamas group and some solo work. And in current work that's going on now, we now know K1 of E2. And it seems likely that we're going to start to get more information about these higher K groups. So that's kind of the state of the field at the moment, is that we're making progress and extending our computational knowledge of these groups in this direction, which is a fun and productive direction because this direction has been very interesting, but it's very hard. And in a sense, the techniques that we're using in this direction are actually the same as the techniques used in this direction. The only thing that changes is which groups are you taking the homology of. So over here, you have easier groups to work with. And as you move to the right, the groups get harder.
So, where you do algebraic know the higher K group of the two-triplex case? What's it going to tell you to know those higher K groups?
Whereas it gives you information about the homology of the automorphism group.
You don't actually see it. It's something about the symmetries.
It's something about?
The symmetries of the space, then, you're saying.
That's right, yeah. So for instance, by computing all of these, you get all of the homology of IET. So we now have a formula for the homology of IET. Actually, this guy, Owen Tanner, got the formula first. But you can recover that formula from this calculation.
Usually the motivation for computing higher K groups or rings is that there's a range of complex sequences that allow you to compute lower K localization, or are there results like that for this congruence? Like if I know K5 of E2, can I say something about K4 of E3?
Well, there is product and coproduct structure that lets you go between them. I don't know about localization sequences specifically. That would be a good thing. Maybe I'll add that to the problem session this afternoon. Maybe we can think about that. All right. So since I don't have a ton of time left, let me just say there's a couple of big banks of theorems here. And one of them comes from the Cool Mamas group. One of them comes from this collaboration with Big Mamas and some solo work. So one of the big things that we prove here is a homological stability theorem. So it actually tells us that when I go from a smaller polytope to a larger one, the homology actually doesn't change. So when I go from aught P to aught of P disjoint union R, that map on homology is actually an isomorphism. And so that tells us that actually the K groups are not just telling us about the stable homology of these groups, they're just straight up telling us about the homology of these groups. This has lots of cool corollaries. So for instance, corollary, a K1 invariant is determined by, or let me say it this way, to give a K1 invariant, you only need one homomorphism from aught P to one abelian group A for one polytope P. As soon as you give a single homomorphism like that, it automatically extends to a compatible homomorphism for all the other polytopes in your geometry. Right? So this apparently very rigid, highly structured thing, or this impossible to construct thing, is actually not impossible to construct. And of course, there's now you can see what the universal one should be. Right? The universal one is the abelianization.
Mm-hmm. Doesn't that just induce a sort of a like a lambda map on the K theory over and up?
Yep. Yep, those do induce maps on the K theory.
That's what you're saying there? Is that
those are, yeah, in fact, you can use K theory and split it up into different weights using that map according to what power of 2 the doubling map acts like. So that helps you decompose K groups. Yeah. So another corollary of this is this universal K1 invariant is the abelianization of aught P for any polytope P. Oh, I have to say here, P is not the empty polytope. Again, that's a thing that some jokers point out when I'm doing talks like this.
Technically not allowing anything anyway, because there should be all I think we would never not in the beginning rule this out.
Oh, hey, you're right. According to the definition I gave, well, no, so I defined a polytope to be any finite union of convex polytopes. And when I say finite union, I usually include the empty union in that. So I do have to explicitly not include that, because I'm a true disciple of the empty set, and I will not betray I will not betray the empty set, even to be right about something. OK. So that's one cool fact, is that this universal K1 group is actually just the abelianization of any of these groups. So they're all possibly different groups, but they all magically have the same abelianization. So the other big theorem, and this is a result of this Big Mama's work and some solo work on top of it, is that there's a formula for these higher K groups in terms of group homology. So I'll just tell you about the Euclidean case. So the K groups of Euclidean geometry are given by the group homology of whatever your symmetry group is, but you have to make it discrete. And then it acts on this thing called the polytope module. I guess actually, G could be anything here. Maybe I should tensor this with the rationals, just to be safe. And then this is not necessary if the translation group is contained in G, because then in that case, it turns out these are already rational, and they just agree. OK, so this is the polytope module. This is also called the affine-Steinberg module, if you've heard of that kind of thing. So this is a group that's generated by polytopes. And we have the additivity relation like this. But that's it. We don't have any relation that allows us to move them around. So you can think of this as some sort of group of measures that are generated by indicator functions of your polytopes. So this gives you a formula. It says you can get the higher K groups by just computing some homology of groups made discrete. How hard could that be? Well, it turns out quite hard. This formula applies to K0 as well. In fact, this formula was known before our work, more classically, and this is the way that people were earlier able to say things about K0. They would turn it into a more algebraic question like this, and then make some arguments involving group homology. So in some sense, what we're doing is we're showing how the classical techniques for K0 can be lifted and describe the higher K groups as well. So unfortunately, I don't have time to walk you through this calculation, but you can use this to show that the K groups of E1 with translations are all given by exterior powers over the rationals of the reals. So you can compute that directly from this description. So in particular, K0 is the reals. K1 is the reals wedge the reals. K2 is the reals wedge the reals wedge the reals, and so on. So that's what all the higher K groups are here. You could also pass to all isometries. If you do that, all that happens is the odd K groups die. So the odd K groups become 0, and the even ones are the same as this. So this tells us that the homology of the group of interval exchange transformations is the free graded commutative algebra on the positive exterior powers of the reals. So that's that higher K theory, doing a computation and deducing something about a group from it. All right. Just going to keep moving through the Cayley graph of this scissors automorphism group of the blackboard.
Just like taking two translations, making
Yeah, the group structure is if I have two scissors automorphisms, I think of it as a scissors automorphism of P disjoint union P. And then I use the canonical isomorphism between that and automorphisms of P again to bring this back down to a class in the homology of automorphisms of P. Oh, right, so in the case of intervals, right? So you take two interval exchange transformations. You think of that as a transformation on interval of length 2 instead of 1. And then you use the fact that that has the same homology as the interval of length 1. All right. So you can also do this for K2, or sorry, you can do this for all the K groups of two-dimensional Euclidean geometry, and you get this nice explicit formula in terms of the homology of O2 as a discrete group with coefficients in lambda 2 of R2. Again, that's over the rationals. And there's a little sign there. So that's another corollary of this, of that general formula. You resolve the polytope module, and you get a splitting like this. So you can use this to compute that K0 is R. So this gives you a way of doing that exercise that I gave you midway through the talk. Yeah?
Where's the cube on the right-hand side?
Hmm?
There's a little cube.
Oh, I'm just emphasizing that I'm taking exterior powers as a rational vector space, not as a real vector space.
A little cube, like the small cube. Small cube.
Oh, I'm doing this from memory. Thank you. I forgot this should be 2q plus 2. Thank you. So from this you can compute, so this is actually not too hard, that K0 is R. You can also compute, but this is much harder, that K1 is 0. Much, much harder. I have no pride, and I will just say that I spent 2 to 3 years staring at this homology formula and trying to get K1, and I was unable to do it. And certain modern advances in technology have given me a way of learning how to do it. If you want to find out more, come to the panel this afternoon. I mean, I would have loved to figure it out myself, but I couldn't. And I'm overjoyed to know the answer. You know why I'm so excited to know this? Right? Because this connects back to group theory. So this implies, so using work with all of the author groups that I mentioned at the beginning, combining all these results together, that for all polytopes in 2-dimensional Euclidean geometry that are not, actually, I can drop this assumption. The scissors automorphism group is simple. Right, so why is that? Because its abelianization is equal to this K1 group. So that's using the Cool Mama's work. And then using this calculation, that is given by this homology formula. Turns out there's only one summand in that. And then using the ongoing work, where we used AI to help us, there I said it, to help us figure out how to compute this, that's 0. So that implies that this group is perfect. And then we combine this with an argument that Matt Bryn worked out and told me about, and that now Jin Lee and I are writing up, because Matt's retired and he doesn't care who gets credit for this. Thanks, Matt. That the commutator group of this is simple. This connects to Yasha's mini-course talk, right? Because it basically uses Higman's simplicity criterion to prove this. So now you combine that all together. This should be on the outside. This is equal to its commutator subgroup. Therefore, it's simple. Thanks so much. Huh? Oh, I forgot to mention Thomson's group V. You can get a new proof of Zimik and Wall's theorem that V is acyclic using this. All right, thank you. I'm answering your question now. I'm answering your question. So you can also do this for Thomson's group V, right? So in this case, you're going to take polytopes in E1, but you're going to restrict your vertices to dyadic rationals. So now you get a similar group homology calculation here. You have to compute the homology of the group that acts in this setting. So that's translations by dyadic rationals, and then scalings by powers of 2. And that's going to act on this group, this polytope module. It's defined just as before, but I'm only going to consider intervals whose endpoints are dyadic rationals. You can compute this. So this is a semi-direct product, so you can use like a Hochschild-Sayre spectral sequence and do it in stages. And you end up getting exterior powers of this group over the integers. But this is rank 1, so there's actually only going to be one exterior power. The second and higher ones are going to vanish. OK, so we get rid of that. That gets us the homology with this group. Then we have to mod out by the homology of this group. Well, the generator here acts by scaling by a factor of 2. So now we take a map from this group to itself, scales by 2, and I subtract the identity from that. That's how you take group homology with z coefficients. 2 minus 1 is 1, and 1 is an isomorphism. And so therefore, this complex is acyclic. That implies that the k groups are all 0. And by a connection with homology, that implies that the reduced homology of Thomson's group V is 0. So this gives you a way of computing Zhimik and Wall's theorem that V is acyclic. And it's a method of doing it that I really love because it generalizes way past V, right? This is not just about one-dimensional groups. This is about any groups that come about by taking polytopes and cutting and rearranging them. If you can get this kind of cancellation because you're scaling by a factor of 2, you can get something acyclic. So you can use a technique like this to also show that the Bryn-Thompson groups are also acyclic, and to more generally compute the homology of Higman-Thompson groups and various Bryn-Higman-Thompson groups, right? Various groups in this family. Thanks for your question. I was answering a question. That wasn't part of my talk. Thank you.
If we just instead of taking isometry, we just take translations, do you have a similar, how far is this? What do people know?
What do people know? At the K0 level, we actually know translational scissors congruence in all degrees, in all dimensions of Euclidean geometry. I kind of alluded to earlier that the translational case is easier. So therefore, above that, for the higher K groups, we also have a really nice formula. I mean, so in some sense we know it, but I think in some sense we could know it better. If there's some presentation in terms of a large complex, but there's still this outstanding question of if I take the volume and if I take these so-called Hadwiger invariants, are those complete invariants? So that's a question that we're starting to ask now about the higher K groups in the translational case. It's kind of like one of these questions where it seems like there's no reason why this should be true, and yet all the calculations we've done so far are consistent with the idea of it being true. So it'd be really cool if it ends up being true, because it's one of these things that really shouldn't be, but somehow, the math gods conspire and make it true.
Do you know if these scissor congruence algorithm groups carry Polish topologies?
Polish topologies. I don't know. Let's talk about this more. That sounds like an interesting idea. Yeah, at the moment I don't. So there are profinite spaces that they act on that we really like, but in terms of topology on the groups themselves, I haven't yet encountered a meaningful or useful topology to use on these groups, and I'd be interested if there is one.
I have a quick question.
Yeah.
Is there analog of maybe curve complex for polytope or polygons on which automorphism would be apt?
An analog of the curve complex. There is, in this homological stability work, there are these complexes of scissors embeddings that we prove are highly connected in order to do this homological stability argument. Yeah, something like I have some smaller polytope P and I have some larger one Q. And then a vertex in my complex is some scissors embedding of P into Q. So I actually can cut it up. It doesn't all have to be in one piece like that. And then if I have multiple vertices, they span a simplex if they're disjoint from each other. So that turns out to be a useful complex to think about when you're studying these groups.
Any more questions? All right, thanks, Cary, again.